So let's go for it. This is called exponential logarithmic functions. We're going to cover a whole bunch of ground today. And so we're going to go 4-1, 4-2, and 4-3 hopefully today. So I've got a whole bunch of stuff to do. Just in 4-1, we have to define what in the world are exponential functions, develop some formulas. I'm going to look at some application questions. And I like this chapter because there's a whole bunch of application questions. Exponential functions, logarithmic functions are used quite a bit, particularly in science here. So, we'll click here, just a definition of it here. You got f of x is equal to a to the x, and that right there is the exponential function. Got some conditions. A has to be greater than 0, and then also a can be 1, because if a is 1, and you take powers of 1, what's 1 to the third? 1 to the fourth? 1 to the fifth? It becomes a linear function, so we don't use that one. That doesn't make sense. But anything besides 1. Alright, domain is from negative infinity to positive infinity, which means for x I can plug in any number I like into there. So there's your formula. So let's just kind of do just a quick... I'm going to go through, let's see, probably best. You guys have the example problems in your textbook. I'm going to do the practice problems in class, because you figure you already have the example problems, unless it gives you some other information we don't have. Cool? So I'm going to go between the two here. So 1, 2, 3, 6. So practice problem, there it is. Again, if you look at it, your textbook, you'll see it in your textbook as well. So I'm going to just sort of quickly mention what that is, and then we'll jump to the problem here. So exponential function, it is f of x is 1/4 to the x. And we're going to try to find all these here. F of 2, f of 0, f of negative 1, and then yes, we've got some fractions to deal with as well. So if I'm going a little bit too fast here, always refer back to the textbook for practice problem number 1. At least you see the problem there. Alright, here's our function. We're going to plug in a 2 into the function. And that's an easy one, because if you plug in a 2, you're just really squaring a 1/4. Squaring a 1/4 gets you 1/16. And that's kind of what we're looking at here. Again, we want to take a look at the graphs of it. And then eventually, towards the end of the chapter, we want to be able to solve. F of 0, and you know that any number to the 0 power is 1. Perfect. You got it. That's going to be actually a special point for us as well. Plug in a negative 1, and we should realize what the negative 1 exponent to negative 1 means. Perfect. It means reciprocal, right? So reciprocal of 1/4. Got yourself a 4. And that's going to be an important point for us as well. And then we got the fractions here. So I'll let you guys start the fractions here. Those that just came in, we're going to do 3 sections today. So we're going to go very, very quick. And then I have a lunch meeting as well, so we're going to finish 5-10 minutes early as well here, because I got to go prep for that. So here we go. Faster than fast. Bless you. Alright, 5 halves. How in the world do we do that? So 1/4 to the 5 halves. And if you remember correctly, remember the little 5 on top means the power, and the little 2 means the root. So it's 5th power square root of this. So square root of 1/4, and then we're going to take it to the 5th power. Alright, square root of 1/4. Everybody okay with 1/2? Alright, taking that to the 5th power eventually gets you 1 over 2 times 2 times 2 times 2 times 2, or 1 over 32. Bless you. Cool. Again, I'm going to try to go quickly. If you can keep up, that's fine. If you really need to go back, I go back to the slide as well here. Alright, and the last one here, f of x, or f of negative 3 halves. So So it's a fraction and a negative in the exponent. How do we handle those? Well, got to do the negative first. So the negative means reciprocal, so a reciprocal of 1/4 is a 4. And then we've got to do the fraction in the exponent here. So again, that's going to be a square root of 4, and then we're going to take that to the third power. Square root of 4 is 2. 2 to the third power eventually becomes just an 8. Alright, we do have to review a little bit thing here. Since we have exponential functions, we've got to review exponential rules here. Remember rules from exponents from algebra? If you multiply numbers, all you're going to do is add the exponents. If you divide numbers with the same base, you subtract exponents. And again, maybe if you have a coefficient and a variable or multiple variables in here, and you take it to the x power, the x goes to each and every single one of the coefficients or variables. And this is called the power of power rules here. If you see an x inside the parenthesis, x outside, you're taking the power of a power. What we do is we just multiply the powers together. Again, talked about this here. Any number to the 0 power is going to be a 1. And then the reciprocal rule here. So a to the negative x is a reciprocal here. And technically what it really means is, since 1 to any power is the same thing as 1, you can write it like this or you can write it like this, depending what you need to do. Algebra, we tend to write it like this for algebra purposes. For graphing purposes, we want to write it like this. That'll sort of help us. Cool. Alright. Let's go from there. So I'll give you guys two problems here. What do we do there? Give you a quick minute to decide and do it. So with a, what's going to happen here is that I have a multiplication with a base of 3. Therefore, I'm going to have to add these together. But we know that square root of 8 and square root of 2 cannot be added together unless you have the same exact root. But 8 is 4 times 2. So technically, isn't 8 square root of 8 really 2 root 2? Kind of what happens there. And now we can add these guys together because I have the same exact radical. We call them like radicals. So 2 radical 2 and another radical 2 make 3 radical 2's. There's my simplified version. For b, again, exponent that's inside the radical and an exponent that is outside the radical. We're going to have to multiply those guys together. And in this case, it does reduce. Square root of 16 is actually just a 4, so it really just becomes a to the 4th power. Cool. Alright, next examples, I got to do the examples and the practice problems because they're slightly different from each other. Or at least give you an idea of what to do on the next problem here. Okay, if we're going to graph any kind of function whatsoever, but in this case an exponential function, and we don't know what the graph looks like, we can always set up a little table of values. So we start off with negative 3. 3 to the negative 3 makes a 1/27th. Remember that because of the reciprocal rule. So it's really 1/3 taken to the third power. This is 1/3 taken to the second power, so 1/9. This is just the reciprocal of 3 because you're plugging negative 1 into the x value. And again, any number to the 0 power is 1, and then we take powers of 3 to give us those numbers. Okay. So exponential functions, you're going to hear it a lot. It is a continuous and smooth curve, just like polynomials. So you're going to try to draw a smooth curve that's coming all the way across. Alright, so if you want to put individual points, that's great. And eventually you want to have a graph. Hey, just interestingly enough here, do you guys see any horizontal asymptotes? Just like the rational functions. Sure is right here, right? It can never touch 0. Can't take a number to some kind of power to give you 0. It's not going to work. You can get very, very close to 0, but you're never going to touch 0. So yes, these guys have a horizontal asymptote, but no vertical asymptote, because this can keep on going and going and going. There's never a time when there's a break in our domain. Alright, so yours, f of x to the 2x. Give you guys half a minute or so and make a little table as well. Use the same numbers that the previous problem did, so 2 to the negative third would give you a reciprocal of 2, which is 1/2, and then we're going to take that to the third power, which makes 1/8. Everybody agreed there? And then the rest just sort of follows. 2 to the negative 2 would be a reciprocal of 2, which is 1/2, now squared, so it gives you 1/4. 2 to the negative 1, just the reciprocal of 2, which is 1/2. The rest should be pretty easy, where 2 to the first power is 2, to the second is 4, to the third is 8. Alright, based upon those points, can you make a graph? Alright, the graph should go maybe something like this here, so negative 3 1/8 up, just barely above the x-axis. Negative 2 go a quarter of the way up. Negative 1 you go halfway up, then you go to 0 1. And notice what's going to happen. We're always going to have this little number if we haven't shifted anything over, right? 0, because you plug in any numbers at 0 power is 1. That's going to be a very important point for us. But also you go to 1 2, 2 4, and then 3 8, and then now you can connect them. And then what you're going to do also, which the book does, it does it sometimes, not consistently, but you should put in a horizontal asymptote. You should say, you know what, that it's going to get close to 0 but never touch 0. finishing up, go for it. Alright, now the question is, what happens if I, instead of using a 2 here, what happens if I use a 1/2? Again, what's the change to the graph? And I'm not sure what the graph looks like yet, so I'm going to still make a table. This is actually the example problem. So I take the reciprocal of 2 and I use that as my function. And I kind of see what's going to happen between the two graphs here. Plug in a -3. This time, reciprocal of 1/2 is 2, and 2 taken to the third power is an 8. -2 in here, reciprocal of 1/2 is a 2, 2 squared is a 4. So again, as you do that, what has changed? What's going on here? What happens with looking at a reciprocal? And so, again, the example problem that we're given, that right there, isn't that really, from the previous graph, isn't that really just a reflection about the y-axis? That's kind of what we have here. Alright, we'll look at those later as we think about transformations, right, in a little while here. But just know, if you have a reciprocal of that, really what you have is you have a reflection about the y-axis. Alright, our problem is this. Can you graph for me y is equal to 1/3 to the x power? And really what we're looking at graphs where the a value, the base, is actually between 0 and 1. On the previous example and practice problem, we looked at when the base is greater than 1. So what's the switch? What happens there? Alright, make yourself a little table. It's to the 1/3. Answers here, see if you guys agree with me. So again, 1/3 taken to the -3, a reciprocal of 1/3 is 3, and then 3 times 3 times another 3 is 27. That's your first number. And again, let me give you the rest of the answers. Alright, and the graph should look like this here. Now notice we're going down this time. And so we have something that looks like this. And again, don't forget the horizontal asymptote as well. Alright, so what we really have is these are called decay curves, because what's happening is they're actually going down. And then the ones that we have before, anything that's above 1 as your base, those are called growth curves, because then it's going up. And that's sort of the distinction between the two. So exponential growth, and then we have exponential decay. And all depends on that little number here. If that number is between 0 and 1, we have a decay curve on our hands. If it's greater than 1, we have a growth curve on our hands. So you think about population growth, you think of bacteria growth, all that stuff. You're looking at this kind of situation. Or if you're looking at Lysol and you're trying to figure out if it's going to kill the germs or not, then you're looking at this decay curve, trying to make sure that those bacteria are actually going to die. Okay, with that, we have a whole bunch of properties about exponential curves. It's on page 396. It just goes and goes. The whole entire page is just properties. So if you want to refer to that. So if we have this, and let's kind of go through it one by one just real quickly here, see if this makes sense based upon the graphs we just did. So f of x is equal to a to the x, and we're looking at the value when a is greater than 0 and a is not equal to 1. What's happening here? The question is, is my domain from negative infinity to positive infinity? Yeah, I can plug in whatever number I want. The range, because it never hits 0, it never goes below 0, the range is above 0 to infinity. And this is the one we didn't sort of see yet here. So f of x plus 1 is equal to a times f of x. What in the world is that? So let's take a look at one example here. Let's use 2x, for example. So if this was, let's just say 3. 2 to the third power, everybody okay with 8? And if I put a 4 in here, 2 to the fourth power would be 16 is good, right? 2 times 2 times 2 times 2 is giving me 16. What this is saying is, if you compare these two numbers here, so if you take this number here, actually no, this number here, which is 16. 16 is really the base, which is a. In this case, it's 2. So in order to get to the next value, all you really do is you multiply by the base again. Or what you can do, really what this works is this right here. If you take the 16 divided by 2, 16 divided by 8, you get your base. So you take any two values, you divide the next one divided by the previous one, you get yourself the base, or the a value each time. Alright, a greater than 1, that is called the growth factor. That's how fast something is growing. And if that's the case, then f is increasing. And these little things right here, let's see, for a to the x, when x is less than 0, it's going to be less than 1. Right at 0, it's going to be equal to 1, that famous point that I was talking about. And anything greater than 1 is going to be when x is greater than 0 or when it's positive. And then limits, you guys should know this here. As x gets bigger, y is going to get bigger. Right? It's because it's growing. It's going up and up and up. And as x goes to negative infinity, what's happening with the y values? They're getting closer and closer to 0. Never touches, but just closer. Okay, if the number is between 0 and 1, like the 1/2 and the 1/3 that we talked about, that is called the decay factor. And it sort of switches, right? It's above. Let me check. Yeah, okay. Sorry, my mistake here. For the growth factor, the graph goes like this, right? It goes like this. So if x is in the negative territory, that means it's going to be above 0. At x equals 0, it's a 1. And at the positive territory for x, it's going to be less than 1. It's always underneath. And again, let's see if this makes sense here. As x goes to negative infinity, y goes to positive infinity. As we go this way, as x goes this way, the graph goes higher. As x goes this way, the graph tends to more and more closer to 0. Next is something we've seen before. Is this a one-to-one function? Yeah, it is. Isn't always increasing? Does it pass the horizontal line test? Absolutely. It passes the horizontal line test, therefore it's a one-to-one function, therefore it does have an inverse. So that's that one. From algebra we should know this here. If you have an equation, you're solving them, and the bases are exactly the same, that means the exponents have to be exactly the same. Okay, this graph does not have any x-intercepts, never crosses the x-axis. And then these are the important points we should look at. So if you look at this graph here, 0, 1 we already talked about. But 0a, so whatever the base is, you're always going to have this graph at the base. So if it's 2 to the x, you get 1 comma 3. It's 2, sorry. If it's 4 to the x, you're going to get a 1 comma 4. On the other hand, you're just going to get its reciprocal on this side. So negative 1, 1 over a. And yes, we do have a horizontal asymptote, which is the x-axis. You should keep on going. There's a whole bunch of stuff here. Let's see. Tell me if you guys think this is true. We did it on the graph here. That little negative in the exponent doesn't really mean it's reciprocal. So when we graphed 1/2 to the x, we could have actually also graphed this right here. And remember, if the x is negative inside the function, doesn't that mean it's reflexive along the y-axis? Right? If you remember transformations from 2.4. Anyways, for anything bigger than 1, it means the graph is strictly increasing, which means it's going higher and higher and higher, doesn't go lower, which we'll talk about next. For intervals, last two here, okay. It means as we look at intervals less than, and we go down to the left, it gets lower and lower and lower each time. Alright, and then the important point that always is here is 0, 1. That's where it's going to intersect the y-axis. Okay. Alright, so let me skip around just a little bit here just to go a little faster. I think we have... Let me see if this is right. Let's go backwards now. We had an example problem, which is not here, but here's what we want to do. We have a graph that goes through these 2 points, 0, 1 and 249. The question is, can I get an equation off that graph? So we've been graphing on the last practice problem. Let's go backwards. Can we get an equation? And same thing here. For b, I know this graph goes through 2, negative 16, 3, 1/2. It looks like this. So maybe it kind of does this right here. Starts curving up. The question is, can I get that? The thing that should come to mind over here, though, notice sometimes we do have x-intercepts. We have x-intercepts if we start making transformations here, right? If we go lower, we will eventually have an x-intercept. We will always have a y-intercept there somewhere. Alright, so let's go for it here. So for the first one, 0, 1 and 249, what we do is we set up a basic exponential function. And there it is. C is a coefficient in front, a is our base, and x is our variable. Alright, so what we do, plug in. So we're just trying to figure out what in the world is C. What in the world is C? And if we plug in a 0, we should get out a 1. So in this case, that f of x, doesn't that become a 1? I'll need to write it like this here. f of x, that's the output. A to the 0. Is that true? So I figured out that C is 1. So first goal is to figure out what is our coefficient. Once we figure that out, we're good to go. We know that's a 1 now, so I don't need to worry about that. Now the question is, what is the A value? A value, so we use this point to figure out the C value. We'll go over here to figure out the A value. So output of 49 is given when there's an input of 2. That should be okay now, right? Take a square root of both sides. And why am I not doing plus or minus? Yeah, the A value has to be positive and not equal to 1 as well. So if that is the case, there it is. Perfect, I got my equation. My equation is, there's a 1 here, which I don't put down, so there's my exponential function. Okay. Sorry, some people are still copying here. Got it? Next slide, of course, the tougher one. If it's going to get there. Too much mathematics even for PowerPoint. So Microsoft can do everything. Alright. Go like this then. There it is, that's the one I want. Yeah. Okay, PowerPoint quit on me here. See if I can find out where I'm at here. Alright, let's start with this one then. B. Can we figure out the equation of this right here? So it goes to negative 216, it goes to 3 1/2. Well, we're going to use 1 point to figure out what our C value is. So let's plug in general exponential function. There it is. And so we get an output of 16 if we have an input of negative 2. Oh, we've got ourselves a little problem now, because I have 2 variables that I'm having right here. It was easy with the 0, because when I plugged in the 0, A became just a 1. A disappeared. This time, there's a C and a A. They both stay here. Okay, gets a little more complicated. Let's go for it here. Let's do this here. Let's solve one variable in terms of another. If we can do that, at least we get something close to it. So let's go ahead and solve for C. So the way we solve for C, since we're in this stage, right, the a to the negative 2 really becomes a to the 2 on the bottom. And we learned this in the last chapter. Let's multiply both sides by a squared. If I do that, a squareds cancel on one side, and I'm left with C equals 16a to the second. least got that. So here's what I'm going to do now. I'm going to plug in the other value here. So let's see. I'm going to plug in setting up the same exact equation all over again. And again, why are we doing this? Because we couldn't get rid of both variables. And if you think about it, if you go back to in your mind something called systems of equations, that's kind of what we're doing. We're solving an exponential system of equations. So output of 1/2 is given when I have an input of 3. In your mind, think about the substitution method of systems of equations. That's kind of what we're doing. Okay, we're going to solve this guy, if we can. Or, you know what we can do? We can put both these guys together. Don't we have 2 equations and 2 variables? Yeah, technically, 2 equations, 2 variables. I could substitute one of the variables with another. So if c is equal to 16a squared, how about if I do this? 1/2 is equal to 16a squared times a to the 3rd. Alright, let's solve this guy here. Let's see. So that'd be a to the 5th, because we got it's a multiplication between the two. So add the exponents. Let's divide by 16, because I'm going to solve. I need to solve for a to the 5th here. All right, divide by 16 or multiply by 1/16 gives you 1/32. And we take the 5th root of 1/32. Anybody with that answer? So you tell me, what is a equal to? 1/2, isn't it? Because 1/2 times 1/2 times 1/2 times 1/2 times 1/2 is 1/32. Now, if it was the 5th root of 32, it would be 2, right? But it's the 5th root of 1/32. Okay, so systems of equations, I substituted, I figured out for one value. Now I have to plug it back in and solve it for the other value. And it doesn't matter which way you want to go. You can go back to this one. The 1/2 is equal to ca to the 3rd, or you can go back to this one. I think I want to do the second one. How's that? 1/4. And 16 times 1/4 is a 4. Is that right? Done. Sheesh. Let's go back over here. Final answer is f of x is equal to 4 a to the x what's my a value? Oh, that's right. I have an a value as well, right? That's not just an a value, it's 1/2 x with the multiplier. That's 4 times 1/2 to the x, where 4 is really the coefficient, that's a multiplier, and then you got the 1/2. Now, how many of you say, Mr. H, I wish I would have read ahead, at least a little bit here, just to make sure. All right, there's always 7 of you that wish you would have done something different. Okay, let's go back up to some application questions here. First of all, something called simple interest. Simple interest is what happens if you get interest only on the money you deposited. That's about it. So we denote interest with I, which kind of makes sense. Principal is just the money that you've put in. That's called P. And then T stands for time. What is the formula for simple interest? This right here. I is equal to PRT. So if you have credit cards, let's see what happens here. A lot of times that is simple interest. So what they do is they take your average daily balance for those 30 or 31 days or whatever it is. They times it towards your interest rate divided by 12, right, because that's per year, and then, no, they actually divide it by 365, and then they multiply it by the number of days in the calendar year. That's why your interest changes a little bit here. The mortgage payments also do the same. It's just interest for that period. Let me see, 1, 2, 3, 4. So again, we're just going to plug in here. Starting at this point, you probably should get a calculator because you'll need a calculator to do this. So practice problem, I'm going to skip the example problem here. So find the amount that will be in the bank if you put in $10,000, deposit simple interest, and you put in there for 2 years at 7.5%. Well, what you're going to use this little formula here. P is equal to I, R, and T. Just need to know each of those variables. Notice R comes in as a decimal, not as a percent, so kind of careful there, you got to convert that. So plug it into the formula, PRT, interest we're going to calculate right now, 10,000 times the R value times the time in terms of years here. And if you do that, again, you're going to have to use a calculator here. It should wind up to be $1,500. Not bad. $10,000 sitting in the bank for 2 years, get you an extra $1,500. Alright. A part of the problem is to figure out what the actual value is. So how much money do you actually have in the bank? So in that case, it's an A value. A is equal to I or P plus I. So it's the principal plus the interest. A means just for the amount that you have, or amount. Again, if you go into business, that's exactly what you're doing. There's a whole class on just interest. How do you calculate interest? And then it gets really fun when you get into compounded interest. You start looking at retirement plans, which for you guys, I don't know if you have that, looked at it yet, that or not. But so you got the principal of 10,000 plus 1,500, and the one that's missing over here, sorry, it's a 1 and a comma. So eventually you get 11,500. Okay, so simple interest just on the money you deposited. That's all you get. Compound interest when things change. Compound interest is you get interest on whatever is there. So the formula, A is equal to P, probably need to know this one, in parentheses 1 plus R to the T. And that is for interest compounded annually. So every single year, once a year. If you have a savings account, most savings accounts, they are compounded quarterly. Some savings accounts are compounded monthly, just depending on how they're done. Again, there's the example problem here. You just plug in values at this point, and then what happens with compounded interest? It's already solved for A, so it already gives you the A value. This is how much you're going to have. So the B part is actually figure out just how much interest you earned. That's going to be a subtraction problem now. So when you deposit $8,000 in the bank at the interest of 7.5%, compound annually, bless you, for 5 years, what do we have? All right. And I'm missing a slide. That's the problem. It's reversed, that's why. Okay. All right, formula. There it is. And we just plug in values. And again, you probably need a calculator. You're going to have to get a calculator at this point because you're going to have to multiply. So this means you're going to multiply 1.075 times a 1.075 times another 1.705 and again and again. So you're doing it 5 times. After you do that 5 times, then you multiply times the 800. So what really is happening is the first year it's $8,000. The second year you're getting interest on the $8,000 plus the interest you earned from the previous year. And then the third year you're getting interest on the $8,000 plus the interest you earned for the last 2 years. So there's now a little growth here that's happening here. All right. Calculator wise, what you should have is like something like this: 8,000 in parentheses 1.075, and then again the little caret to the 5th. All right, and to the nearest cent. That's what we usually do. So 11,485.05. What's some fun stuff here? There's a famous story in history. Benjamin Franklin. Well, let me back up. Albert Einstein. He actually said compound interest should be one of the wonders of the world because it's so fascinating how it works. And so Benjamin Franklin got a hold of that and said, you know what, that's kind of interesting. So what he did is he went to the bank in Philadelphia and he said, you know what, I would like to put in, let's just say it was $500. And I'd like to keep it inside here for 250 years. And after that, I would like to cash it out and give all the proceeds to the city of Philadelphia. Like, okay. So whoever took the money took it. They signed the agreement and everything was great and all done. And so 50 years down the road, a new bank president took over, was looking after all the funds and looked at this one and said, oh, that's kind of unusual. So he started calculating how much in 250 years, because this is what happens with interest. Eventually, the $8,000 earns $8,000 of interest, right? And then you're getting interest upon now $16,000. And then as soon as that grows, you're going to get now interest on $32,000. So eventually, it's an exponential curve. It goes like this, right? Start off with this much, and after a while, it's going to go like this. And so they caught it 50 years later, but as soon as you reach about 70 years, 80 years, that's when interest really starts picking up, because now you've sort of doubled your money or tripled your money by now. And so could you imagine what's going to happen at 250 years? So the bank president calculated it, and if that was going to go to fruition, the bank would have owed $15,000 trillion to the city of Philadelphia. I mean, it was crazy amount. So the bank president said, no. Called Benjamin Franklin back in and said, we're going to give you interest here, and we're going to close off the account because they didn't want to owe that much money. So I used to teach the business math class that's after this class at Fresno City, and so we calculated that if you are at 15 years of age put in $15,000 into an account and just let it sit there, again, at the time you're 70, you should have that much money sitting there because of the interest that's going to grow and grow eventually. It's going to take that long. But here's a weird thing. If you wait till you're age 22, again, at age 15, you put in 15 grand, you leave it alone, don't touch it ever, don't touch for so many years. If you start off at age 22, you're going to have to put in $1,500 each month until you get to 70. In order to get that $1 million. It's those extra 7 years right at the end, right over here. It's those extra 7 years. That's you're getting so much interest because now your interest is earning interest. That's gonna compound interest. But anyways, fascinating stuff. How that all works. Anyways, we're losing time here. Let's get to it. So the interest formula. The only issue is we don't compound stuff annually. Most of the time it's compounded like, again, savings account. That's going to be compounded quarterly or monthly. A checking account, if it bears interest, that has to be compounded monthly usually. And so we have the little formula slightly different, but this is the number of compoundings per year. And then notice that now it's an NT, because now you're getting interest on that interest per month as opposed to per year. So the formula slightly changes. And let's not do all of them because there's a whole bunch of them here. Skip around just so we can make sense here. It's 42. Practice problem number 8. You have $5,000 deposited. It pays 6.5% annual interest. Find the future value. Let's do just two different ones here. Let's do 1 and 2. Actually, no. Let's do 1 and then let's do monthly. 1 and 4. So we have this, again, this formula here. N is the number of compoundings per year. And so if we have $5,000, 1 plus, again, it's our interest rate of 6.5%. And then because it is compounded one time per year, we divide it by 1. Essentially, it's the same formula that we had before. Right? Because if you are only compounding once a year, you're compounding annually. And so, you should get $5,325 bucks. Not bad. $325 in a year. Letting the 5,000 sit there. Okay, what happens if we do it monthly? So in this case, we're going to divide the .065 by 12, because now every single month we're only getting a 1/12 of that interest. At the same time, we've compounded 12 times in a single year, so it's 12 times 1. And again, if you stick it in there for 3 years, so you're going to put 12 times 3. 20 years, 12 times 20. And it makes no sense to calculate this anymore. So what you're going to do is you're going to have to just put it in the calculator just like this. So 500 in parentheses 1 plus 0.056 divided by 12, and then take that to the 12th power. All right, in this case, not much, huh? Because in the last one we had 320. Oh, sorry, we had $325, right? Now we have $334.86. So by making the money compound monthly as opposed to annually, we actually gained almost $10 per year. Thank you. And right now it doesn't make that much sense. Thank you. An extra. Thank you. I think that should be the last one. Okay. An extra $10 per year, not that much, but it's the fact that eventually it's going to, that $10 is going to add another extra interest later on. So that's where the investment happens here. Okay. Gee whiz. Okay. Allergic to mathematics here today. Or to one of you. Okay. What happens if we go backwards? We're going to invest $9,000. Thank you. At the end, we're going to want to have $20,000, and we want to do it in 8 years. If you know the bank is going to compound a monthly, we want to find the R value that's going to make that true. So what's the interest rate? When I was going to Fresno State, I was working at Bank of America as a telephone reception person, teleservices, when you call in to find out your balance or something. And during those years, mid-1990s, I couldn't quite figure out how come people were asking what is called certificate of deposit. It's a CD. You just say, I'm going to lock in this amount of time of money, and I'm going to wait. Can't touch the money for like 2 years, or you set the time limit, 9 months or 20 years, whatever you like. But the bank promises to give you that amount for that amount of money, and then you just cash it out. And so I couldn't figure out how come people were calling trying to find the interest rate, because in the 1990s the interest rate for a CD was, which means the money they're going to give you, compounded monthly. So it was in the neighborhood, the lowest was about 8% and the highest was about 11%. Now if you go to the bank, anybody know the interest rate on a CD? It's about 1.4%. So hindsight, like, wow, I should have put something away. So let's go for it. This was going to be a tough one here because it's going to go backwards here. So there's our formula. But at the end, we want $20,000. We have $9,000 to start with. We don't know what the interest rate is, but we know we're compounding it monthly. So there's your 12, and then we're going to do it for 8 years. So now it becomes an algebra problem here. Got to figure out how's that going to happen. Alright, let's see, if we divide both sides by 9,000, we can get rid of 0, so now it becomes 20 over 9. We're good there? And that would be, let's see, everything else stays the same except for 12 times 8 is 96. Alright, this is a fun one. Look at this. We're going to solve for r. So are we going to take actually the 96th root of 20 over 9? That goes away, so it's 20 over 9. And it's probably easier to write it as a exponent. So everything else went away on the other side, so this is 1 plus r over 12. let's see, how about subtract 1 from both sides, so 20 over 9 to the 1 over 96, subtract 1 gives you equal to r over 12. And one final thing to do, how about let's multiply both sides by 12, finally get r by itself. Now I got parentheses there, so might as well put it in brackets. And then that one is what we're going to have to type into the calculator. So let's see, at what percent 8 years would give us 20 grand if we start off with 9, so a little bit over double our money here. And so the formula that we're looking at is like this, and here's the calculator equivalent of it. You need the extra parentheses in here. Bless you. And we do have an answer there. The answer is approximately a little bit over 10% to make that happen. These days at 1%, not going to do it in your lifetime. Okay, maybe towards the end of your life. It would be kind of interesting to find out. Quickly jot it down to see. So about a little over 10% to make that happen. So we're solving for r. Now it's an algebra problem on our hands. Okay, so we have annually. We did monthly as well, just to give you that 12. But sometimes, especially something called inflation. Inflation doesn't have a compounding anytime. Inflation actually compounds all the time. So 20 years ago, bread was worth $2. Now it's worth $2.50 or $2.50. How much inflation has there been? And that's the problem. So we don't want to compound it monthly. We want to figure out a way that it compounds it instantaneously or all the time. The other book that we had, it made you look at it from monthly, then it went down to daily, then it went down to every hour, every minute, every second. And so we had to do a whole big humongous formula to get down to a certain place here. So what we have is this right here. This little formula, again, don't need to know this yet here. We have something called E, but it's 1 plus 1 over H. Doesn't that look like the little let me explain it a little bit better here. So 1 is that little number in front. If you think about this here, this is 100%. That's kind of what we're looking at. 100% interest. And H is the number of compoundings, right? And then H times 1, which means number of compoundings per year. And so what we do, it is on page, I wasn't able to copy and paste it here. So let me find it. It's on page 402. And what we do is we just make these compoundings more often. So we could start off monthly. Monthly would be 12 and 12. Daily would be 365 and 365. So as we increase this H value, they make it bigger and bigger and bigger and bigger. So then we're compounding every single second. They were compounding every single millisecond. It's kind of interesting. What happens is, this number right here doesn't go to 1 million. It actually goes to about 2.71828 blah blah blah. It goes to this number here. So it reaches, almost like it reaches a limit. It reaches a horizontal asymptote. So as H gets bigger and bigger, if you want to sort of see a graph of it here, here's 1, 2, and 3. And you have something that looks like this happens. As H gets bigger and bigger, let's say H is a million over here. The graph starts off with 2 right here, and it kind of goes like this to that number right there. It just doesn't go beyond that number. So what is this saying? It's saying as if I am compounding money every single millisecond of my life. The highest interest I'm ever going to have is 2.71828% off that. And so we have this little formula. This is called continuously compounded interest or continuous compounded interest. And again, the best example is inflation. Inflation compounds all the time. So let's take a look at one here. And again, just a practice problem here. I think it's this one here. So say you have $9,000 to invest and at 6%, but now it is compounded continuously. That's the word there. And also it's compounded for 8 years and 3 months. Give you a little flavor for half of a year, or a quarter of a year, a piece of a year here. So how do we do that? So there's your principal, which you invested. You got the E value now. And then everything else is inside the exponent. So there's my 6%, and there is 8 years and 3 months. 3 months is about a quarter of a year. Yeah, it's exactly a quarter of a year. 3 out of 12. So 0.25. So again, having a calculator, so at this point you might as well bring a calculator to class. At least something that can do exponents. If you have a graphing calculator, that's great. Go for it here, but as far as graphing is concerned, I want to see if you can do it by hand. For these sort of calculations, that's kind of what a calculator will be used for. Alright, what you need is you need an extra parenthesis right here, and you need an extra parenthesis right here when you put it into a calculator. So you got this one here, and this one, because you want to multiply the 0.06 times 8.25. If you don't do that, then it becomes a different problem. So don't forget to put in a double parenthesis as you plug it in. Okay, I'm going to go slightly a little faster here now. But talking about the little E there, this E could also become a base, right? In fact, it was a base on the previous problem, e to the x. So let's use this as the base, as opposed to a 1 or a 2 or a 3 or a 4. And this guy is called a natural exponential function. Why is it that? Because whenever we do a lot of applications with population growth, with growth of anything, or decay of a lot of stuff that's happening all the time, oftentimes E turns out to be a pretty good way to model that behavior. So sometimes called the natural exponential function because it occurs in nature quite a bit. Okay, so if we make a table, and so what we do, if you need to do it by hand, we approximate this by being about 2.7. That's kind of sort of becomes your multiplier. It's 2.7. So it's in between 2 and 3. So what the graph looks like. The graph looks like this. So there's my 2 to the x that we graphed earlier is blue, 3 to the x that we saw earlier, and this is e to the x is, again, it's because it's approximately 2.7 to the x. It's in between the 2 and the 3. What you also should notice, kind of interestingly enough, is the blue. Notice the blue line is the top line, and then when you get to 0, 1, it becomes the lower line of the two. So then you got 3 to the x, which is the highest line here, actually is the lowest line underneath here. So they switch right at this point here. Because you figure 1/2 is higher than 1/3, but when you go to this side, 3 is higher than 2. So they're going to switch positions there. Okay. Almost done with this section here. Let's see how we do it. Let's do an example here from your textbook. I'm going to start going with transformations here. So what we want to do here, if you're graphing it yourself, this will be approximately 2.7. So it's 1, 2.7 when you graph them. 0, 1 is always going to be there. And this one, anybody real quick here? Put down, let's see, 1 divided by 2.7. What's that going to give us? 1 divided by 2.7. 0.3 37, so we're going to approximate this by about 0.4 if you're doing it by hand. We're good there? That one, the book doesn't show you, but you should be approximating it that way. So important points for e to the x, if we're talking about approximate values, we're talking about negative 1.4, 0, 1, that's usual, and then 1, comma 2.7. That's 3 points we're going to sort of use and manipulate. But before we do that, real quick here, tell me, using transformations, think back to chapter 2, what is the 2 doing to this at the end? Yep. Remember the number at the end tells you go up or down? Because this is a minus 1, what's this doing to the graph? Cool. So we have this graph here. All we've got to do is we're going to go to the right 1 time, or we're going to go up 2. That's kind of the shift here. So to the right 1 unit, there we did. Now we're at 0.4, and then we're going to go up 2 units. Now we're at 1, 1. We're going to go up 2 units, and here we're going to go up 2 units, so eventually you get here. And notice, if it's off the x-axis, you really want to put in a horizontal asymptote, because you're saying it's never going to touch y equals 2. Okay, for our purposes, can we graph this guy? That was the example problem. Let's look at the practice problem now. Alright, so let's see. Let's think about the transformations first here. So, what's this guy going to do? It's a reflection, but about what? Remember we talked about the y-axis is this guy as being the negative, right? So if it's negative inside the function, we've got y-axis symmetry. If it's negative outside, okay. What is this guy going to do? We got a shift right, and we have a shift down. So let's kind of do this one. All right, there's my graph. And let's see, first graphing e to the x. So there's my points there. Should be a little 1 right here. Do it in blue. Negative 1.4, 0, 1, we know that one. And this is 1, comma 2.7. Next step is we're going to put in the reflection, so the little negative here. So now instead of it being a negative 1.4, now we're at negative 1, negative 0.4. We're good? Putting in the reflections in red. Alright, once we got those, let's see what I did here. Put those in. So I'm going to, so it doesn't get too messy here, I'm going to redo it on a different graph here. Once you get to this point, you're almost done. because you can probably do a horizontal shift and a vertical shift at the same time. Right? So look at this here. We're going to go 1 to the right and 2 down from each of these points. So let me redo it here. There's my red points here. So 1 to the right, and then we go 2 down. Alright, and because we went down 2, we do have a horizontal asymptote. Now, can we get those points? What are those points? Can't really draw it on here. So I got a 0, comma, negative 0.4 minus 2. So everybody okay with that point? This one went down to 1, and it was originally at 1, negative 1 now. Minus 2 more would make a negative 3. And then the next point, which is at 1, let's see, negative 2.7, went over 1 to the 2, and then we went down 2 more, so negative 4.7. Will that work for those 3 points? Bless you, bless you. Cool. Or that. Okay, and I'm debating here. Okay, I'm going to try to get through the next section as much as possible here. So there's 2 example problems. One is about population growth. The other one is about depreciation of car values or boat values. I'm going to skip those 2. Again, they're applications. If you want to look at them, go for it. They're pretty cool here. But this is the exponential growth function, where you have what you start off with, which is a sub 0. Then you have e, and then you have kt. So k is the growth factor, which you're going to have to figure out for one particular problem, and then t is how much time you need. Well, I guess we could do just do one example from the textbook so we have it here. So in the year 2000, human population of the world was approximately this much. Assume that annual growth rate even from 1990 onward was about this much per. So using the model, figure out how much would be the world's population in 2030. So again, we're starting off in 1990. But we know one value. We know this value here. We know that in the year 2000 it was 6.08 billion. So what we have to do first is figure out what the k value. The k value is already given here. So the year 2000 corresponds to t is equal to 0. So if that is the case, then this is what we start off with. This is the initial amount we have. There's my growth factor. Sometimes we have to find it, sometimes it's given, and then again, looking at 30 years later, we plug it in. So it should be about 9.5 billion people by then, if the growth factor is true.